Today we're going to be looking at the next section, which still has a lot to do with limits, but in this case focuses on continuity as well as one of our first theorems. We're going to talk about intermediate value theorem. Before I get into that, there is, I think, there was a couple problems that definitely appear to be a little bit difficult in the homework, and I'm just going to quickly review those limits that people tended to struggle with. One of those problems looks something like this. So once again, this is just review that problem. Limit as x approaches infinity of 1/5 minus e to the x 6e to the x plus 5. So this does not look like many of the examples I did in the last lecture. However, it can be dealt with similarly. So by similarly, what I mean is we're going to sort of look at it kind of like it's a rational function, and to do that we're going to make this one single fraction first. It's a pretty simple denominator situation. We're just going to multiply this over to here, multiply this over to here, have a common denominator of 5 times 6e to the x plus 5. So in our numerator we're going to have 6e to the x plus 5. 5 times that is going to give us 5e to the x, and then in the denominator 5 times 6e to the x plus 5. Maybe I shouldn't skip over that algebraic step because I know how wonderful your algebra skills are, but I did it. We're going to simplify the top of this really quick. So we've got limit as x approaches infinity of just a single e to the x plus 5 on the top now, and then 5 times 6e to the x plus 5 on the bottom. And now we obviously are not going to be able to plug infinity in here. That's not going to help us. We probably don't want to try and graph this unless we have a calculator or are feeling graphical. Yeah, that's a thing. So instead, I'm going to deal with it as if it's a rational function by dividing everything by the quote highest power. There isn't a highest power here, but there is an e to the x. So I'm going to divide everything by e to the x. Just before I do that, I want to multiply through this 5 here into the denominator. That's going to give us 30e to the x plus 25. And now I'm going to go ahead and do that transformation I've been talking about. Divide everything by e to the x. So e to the x over e to the x, I'm going to have 5 over e to the x. I'm going to have 30e to the x over e to the x, and then 25 over e to the x. Notice that there's going to be some things that simplify, right? This is going to turn into 1. Those e to the x's are going to go away. These are going to stay as fractions. And I'm going to rewrite this just over here. Don't follow me this way. I'll have the limit as x approaches infinity of 1 plus 5 over e to the x divided by 30 plus 25 over e to the x. So what do we got here? Well, we do have a situation similar to that first example from the last lecture, in that if we sort of plug in or think about plugging in infinity to this denominator here, we're going to have e to the infinity, which is just going to be a really big number. 5 over a really large number, an infinitely large number, will eventually proceed towards 0 as a fraction. Similarly, 25 over a huge number is also going to proceed towards 0. And so notice what we're left with then is just the limit as x approaches infinity of 1 over 30, which is a constant or a constant function. So our limit is just going to be 1 over 30. Probably a much easier than maybe whatever method you have chose to go with in the first place based off of my feedback, but not that difficult if you choose to go about it this way. So there's that. I'm going to go ahead and get rid of that. And we're going to go and move on to what we're here today for, which is continuity and IVT. So we've talked about continuity before, right? We talked about it in pre-calculus, so I'm not going to spend too much time on it. But we noted that continuity needs to be stated in a specific way. We want to state that a function or some f of x is continuous, let's say at some value, let's say a, if the following is true, right? So one thing is that f of a exists or is defined, right? So in other words, if I plug in a to the function, it spits out some f of a, some y value. A has to be in the domain of the function. If it's not in the domain of the function, then there's no real point in trying to talk about its continuity. The second thing that you want to state is that the limit as x approaches a of this function exists. It also exists, right? This seems a little bit odd. Some people immediately say, well, if it's defined, if it actually exists on the graph, then how does the limit not exist? And there are circumstances in which that happens, and we'll take a look at some of those today. Almost always it's going to happen with a piecewise function or some other sort of situation like that. But let's just keep listing these conditions for now. So we state that f of a, or the y value, exists. We state that the limit exists. And lastly, we need to show that the limit as x approaches a of this function is equal to the y value f of a. These are the necessary qualifications for something to be continuous, and these conditions are super necessary, especially for the AP board when you're trying to show continuity. And so they're not only worth writing down, but you should write them down. That said, let's look at a specific circumstance so that we can make this clear, like make clear what is actually being said here. Continuity in general is not something that's difficult to either define or visualize. That said, the conditions for it are usually what sort of trip people up. So let's just go ahead and make a quick graph here just to sort of make obvious what I'm trying to say. So here's some random f of x. Who knows what this is? It doesn't really matter what this is. Looking at this graph, most students will tell me right away that there are two different places where this graph is discontinuous. You can see it's discontinuous here at this open circle. You can see it's discontinuous here at this open circle. Now, if we were to talk about the limits, however, at these values, it's not that the limit doesn't exist there. In fact, there is a limit that exists there. If we were to ask about the limit as x approaches 1 for this function, we would state that that limit is equal to 2, right? As we approach 1 from both left and right, we approach y equals 2. Similarly, if we were to ask about the limit as x approaches 5 for this function, we can see that we also approach 2. My graph isn't amazing, but the point is that there is a limit at each of these values. The question that you have to ask yourself then would be, according to those conditions, is there a y value there? Well, is there a y value for x equals 1? In other words, does f of 1 exist? I don't think so, right? There's no y value here. There's no defined point anywhere. And so that's an issue, right? There's a limit, but there's no y value. And because of that, we know that this thing is discontinuous. And we know it's discontinuous just by looking at it anyway, but there's a point to be made here. The point is that if you look here at x equals 5, the question is, does f of 5 exist? Well, actually, f of 5 does exist, right? F of 5 is up here at 4. You can see that. In other words, there's a y value there. The problem, though, is that in this case, the y value and the limit don't match, right? You can see that the y value is 4, but the limit is 2. The continuous behavior of the graph isn't actually found where the y value is. So this is still discontinuous. Even though we have both a y value and a limit. In order for something to be fully continuous, these values need to match. And by need to match, I mean really what we need is a graph that is just fully continuous at that value. Take, for instance, a graph that everyone loves or knows, f of x equals x squared, which has no discontinuities. If you were to investigate any value on this graph, and I'm just going to evaluate this particular point 2, 4, you can see that f of 2 is equal to 4. You would also state that the limit as x approaches 2 of this function is equal to 4. And notice that both of these things happen to match, right? The limit is equal to the y value here. And so you can state that f of x is continuous at the x value 2. It's because these match that we call it continuous, or that the graph happens to be continuous. So that's pretty important to note. It's not always necessary to look at a graph, though a lot of the time having a graph is useful. let's just look at a couple circumstances to make this point fully, but it's this sort of theory or system of logic here, which is kind of important for us. That's why I'm going over it as much as I am. Let's just sort of look at, I don't know, let's say we've got some function. Let's say we've got g of x. Let's say g of x is x squared minus x minus 2 over x minus 2. And let's go ahead and state that this is a piecewise function. And maybe we've got 2 here if x is equal to 2. And let's say this is the case if x does not equal 2, for sure. Choosing that value because we obviously have a discontinuity in the denominator here. Now, we could graph this thing if we wanted to and figure out what it looks like. It's not always necessary to do that. We can see that there's an issue at 2, right? There's obviously a discontinuity there, so we should investigate that. In order to investigate it, I'm just going to quickly figure out what's going on here with this function by factoring the numerator, seeing if it cancels with the denominator somehow. Everybody loves to factor. That's a joke, but you know what I mean. I'm thinking that this is going to be a -2 and a +1. Am I correct about that? Seems like it. These are going to cancel, and it looks like I'm going to be left with f of x equals x plus 1 with a hole at x equals 2 and y equals 3. Now, what that means is my graph, generally speaking, and this is a pretty easy type of graph to make, so I may as well just make it. I've got a y-intercept at 1, and let's add ourselves another point here, giving our hole at 2, 3. Whoop. Sorry about that. That should be straight, but it's not. And notice, because this is piecewise, we've got a y value being produced, or a point at 2, 2. So here's what our circumstance looks like. Now, just the fact that we did this math and notice that there was a hole at 2, 3, and that the hole wasn't being filled in at 2, 3, indicates to me, without making any graph, that this is probably not going to be continuous. But noticing using the graph itself, that makes it very obvious, right? You can see that if we're listing our conditions for continuity, question mark, does the y value exist? Yeah, the y value exists. F of 2 is equal to 2. That's from this part here. What's the limit? Well, the limit as x approaches 2 for this function, either based off the graph or using this information from the hole, is equal to 3. Do those match? No, they don't, right? You can state f of 2 does not equal the limit as x approaches 2 of the function, and so f of x is discontinuous at, in this case, x equals 2. All that information is sort of necessary if you're showing that in a free response. Obviously, that wouldn't be necessary in a multiple choice circumstance, but sometimes it's useful to figure that out. So I don't think that I need to do too much more with continuity because we've covered this in the past, but I just want to make note the type of procedure and thought process you should be going through. All right, so now we're going to talk about something else. This is a little different, and not something we've talked about before, and that's the intermediate value theorem. So let's go ahead and list that out. I can't remember what example this is. I might be screwing this up, but let's just say for intermediate value theorem, what I'll from now on probably just call the IVT. That's supposed to be a V, not a U. And before we talk about exactly sort of, the conditions and everything for this, let's just look at the idea intuitively and talk about it. And then after that, we can sort of be a little bit more formal. Let's just say I had a graph. Let's say my graph looks something like this. It doesn't really matter what it is. Let's say this is A and F of A. Let's say this is B and F of B. And let's put, well, I guess I already put it there. So let's go A and then B. And then let's do something with it. I don't know exactly. We'll do some curvature here. That looks a little steep, but whatever. And then let's just say there's some sort of random value C in here somewhere. So what are we looking at with intermediate value theorem? Well, really what we're saying is something like this. Let's say I know that A comma f of A is a point on this graph, and I know that B comma f of B is a point on this graph. In other words, I know I've got this point, and I know I've got this point, but let's say that's all the information I know. And I guess to make this maybe a little bit more intuitive, let's just actually assign values to A and f of A. Let's just say f of A is 2, and let's just say f of B is 30, right? So I know f of A is 2, I know f of B is 30. Let's say I also know that this function, what I'm calling f of x, is continuous on this interval. So let's say, is that how you spell continuous? No, it's not. F of x is continuous from A to B, right? Let's say I know that for sure. So I know that f of A is 2, I know that f of B is 30, and I know the graph is fully continuous from A to B. If I know that that's the case, what I know for sure is that in between A and B, I've got to go from 2 to 30, right? I've got to go 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. with all the values in between until I hit 30, right? I know that that's the case because I know the graph is continuous. It's got to go from here to here. Now, how it goes from here to here is variable. It could do this sort of squiggle that I decided to do randomly here. It could have just gone, you know, at a nice sort of straight arc up to that value. It may have also gone above 30 at some point. That could have been the case. It also could do something different, right? It could rise slowly like this, doing something like this sort of orange graph. The point is that to go from 2 to 30, I have to hit, no matter what, the values in between 2 and 30. I might go below 2, I might go above 30, but that doesn't mean that what I'm saying right now is invalid. It just means that I have to go from 2 to 30, right? I think that's a pretty sort of straightforward conclusion. That would not be the case, however, if, say, the graph was discontinuous. And let me just make that obvious, right? Let's say, for instance, that this graph looked a little bit different. Let's say that there was, I'm still on my eraser. Hold on one second. Let me give us this point back. Let's say we're also looking from 2 to 30, but let's say the graph looked like this, and then it looked like this, and that was my f of x, right? This is a sort of crazy f of x, if you will, but it could be the case. I suppose I should have extended this a little bit out to C so that it's a little bit more intelligible, but let's say here. So these are, of course, disconnected at C. Though we have a value f of A at 2 and a value f of B at 30, this graph is discontinuous, right? So because it's discontinuous, there's a whole lot of values I'm not hitting in between there. So I can't really make any conclusions about the fact that every y value in between 2 and 30 are going to be hit like I did in the last case. And it's important to make note of that. So in other words, for this intermediate value theorem, there are things that have to be true. In other words, the most important piece is that f of x needs to be continuous from A to B. If f of x is continuous from A to B, and then you know f of A is 2 and f of B is 30, then you can make a conclusion that the graph is going to hit values in between 2 and 30. Where exactly, you don't know, but you can definitely conclude that they will be hit. So that was a sort of rough, intuitive approach. Let's look at a specific example. Let's just say we have some random function. I think this is example 5. Let's say we have some polynomial. Let's say f of x is equal to 2x to the third minus 6x squared plus 3x plus 5, right? This is a sort of random example, but we can go ahead and look at that really quick. And so if we're looking at this here, and we want to utilize IBT to show something, one thing we could utilize it to show is where an x-intercept happens to be located. So we would, of course, have to choose values here and be given values or being asked to show something or whatever. So maybe it says show using IVT that there is an x-intercept between, let's say, x equals -10 and x equals +5. So what does that exactly look like? Well, there's a couple things we have to make note of, right? First of all, for IVT, we have to state that the thing's continuous. That was the biggest part about the last example. Now, is f of x continuous here on this interval? Well, it's a polynomial, right? Polynomials are continuous for all real numbers. So f of x is definitely, maybe I should use a different color for this. F of x is definitely continuous on the interval that we care about, in this case, from -10 to 5, right? That's for sure. How are we going to show that there's a 0 in between these things? Well, we're going to use that concept that I just stated a second ago in a pretty broad way. Now, the way that we're going to do that is first by just calculating the y values, right? We're going to calculate f of -10. We're going to calculate f of 5 and see what we get here. I'm going to need to go ahead and do that because, of course, I haven't already because I'm making all these examples up on the spot. But let me go ahead and do that quickly. And let's see if I also calculated quickly enough in my head to do that. Yeah, f of -10 happens to be -2625. And then let's see if I am lucky enough. F of 5 is 120. So I got lucky, right? But f of -10 is -2625. F of 5 is 120. Now, how does this show me that there's an x-intercept in between these two values? Well, if f of x is fully continuous and I go from a y value which is negative to a y value which is positive, what do I have to have done? Well, I have to have crossed the x-axis, right? And if I cross the x-axis, then obviously there's going to be an x-intercept. If I cross the x-axis, I have to hit the x-axis by definition. And so there's for sure, if this function is continuous, an x-intercept somewhere in between -10 and 5. So if I state that the function is continuous, and then I show that these y values are the case, I can say by IVT, or intermediate value theorem, that there is an x-intercept somewhere between -10 and 5. Clearly, that's not at -10 and 5, which is why I switched to parentheses. And so that's for sure the case. Now, this is an existence theorem, so I've shown that it's true somewhere on the interval. Obviously, I didn't state where it is, and I've chosen such large boundaries here, -10 to 5, that I don't really know exactly where it's at. Now, looking at my table on my calculator, there are better values I could have chosen. Obviously, I'm using a calculator, so that's a little bit different. But just so you know, f of -1 is -6, and f of 0 is 5. So notice that from -1 to 0, we go from a negative to a positive number. In other words, there's definitely an x-intercept somewhere in between 0 and -1. That gives me a much better approximation for one of the x-intercepts, at least, of this particular function. I would also guess, just based off of my table, that this may be one of the only x-intercepts. It's a cubic function, but I'm not going to state that that's the case for sure without looking at the graph. So there we are with IVT, and that should be quite useful for some of the problems that you see in this next homework assignment.